So thank you for the introduction again. I'll be talking about a protocol based on transport, which is why I'm not sure why we were scheduled here, but oh well, let's start. So before we actually start, let's get an overview of what a digital signature is for those who are not closely related to the field. A digital signature, as you may have heard, is a basic authentication scheme between a signer and a verifier. And basically what you show is you just prove the authenticity of something you generally possess. And basically what you have is you as the signer have possess a private signing key and there corresponds a public verification key. And whenever you want to sign something, you just use your key to generate a signature. You then send the signature alongside a message to a verifier or anyone from publicly. So if anyone wants to verify that you just possess this message or actually have authenticity. In this case, they use your message alongside with the signature and the verification key and see if everything is correct. And basically what we consider as a security notion in this type of scheme is the idea of unforgeability. No one that do not possess your private signing key can actually replicate your signatures and sign stuff on behalf of you. But whenever we actually consider the idea of unforgeability, we overlook the simplest attack vector we have in this type of scheme. What happens when you just leak your key to someone or someone just gets the hold of your key? Real life is messy, the devices can be compromised, fail. So the moment you can actually lose your access to the signing key, you lose access to all capable of signing as well. How can you resolve this? Through redundancy and the idea of something called threshold signatures. So instead of having one single user trying to sign one single thing, we have multiple users with multiple keys trying to sign the same thing. So a subset of these users can join together and generate the same signature, which then can be verified as well. I'm saying that a subset of users, because based on your scheme, you can just ask everyone to be present as part of the signing, which we also call the idea of a full threshold, or you can just ask them to be a subset of the T of them to be present, then it's called an arbitrary threshold. But the key idea is, even if partially these signers are corrupted, you cannot generate a signature on behalf of someone else. Hence, we capture the idea of threshold unforgeability instead, whereas if there's at least one honest user, no one actually can forge a message on behalf of you. And in this section, we also consider the idea of a passive or active attacker, because now adversity is also part of a key generation rather than trying to find something that they do not possess. Why have I've been rambling about this for 2 minutes? Because apparently adding this type of robust key generation also allows a lot of advanced functionality. The capability of authenticating something over multiple users is a really strong primitive, and there are a lot of applications that are modernly used in our case. The most famous of them, or like actually the most popular one, is the cryptocurrency transactions, where you can just sign a block jointly on a blockchain. And to this popularity, you may also heard that NIST has intentions to actually standardize these threshold algorithms. So there are peaked interest on actually how to thresholdize a lot of the protocols we already have. And to this extent, it has been seen that this is studied extensively to the death in classical settings, where all of the classical signature schemes have their nice threshold counterbalance with nice security properties as well. But here we hear it in the PQ crypto, and we don't care about classic stuff. What about PQ instead? Well, looking at PQ stuff, we see that we are not that lucky. And all of the primitives we are used are either considered some sort of a nonlinear algorithm or non-trivial algorithm that's not easy to thresholdize. And most of the solutions we have rely on heavy machinery, albeit it's either fully homomorphic encryption or multi-party computation, where you have to run the entire circuit over some sort of machinery, which are not efficient. To exemplify this and motivate our main research problem, let's look at the most famous and most popular variant of our post-quantum signature schemes, the lattices one. So basically, a lattice signature scheme follows the blueprint of a Schnorr-like signature, where you have your secret key that is some sort of a short vector. By short, I mean some bounded norm, and your public verification key is both a uniformly random value and a value derived by both from this uniformly value and your secret vector. And what you do is basically Schnorr-like signature, where you just derive your signature randomness, commit to this randomness, derive a challenge from this commitment, and just calculate a response based on this, and that becomes your signature. And when you want to verify this, you just check some bounds, recompute your commitment, and check everything matches. So far, so good, and it's so fine. But the problem here is, unlike classical setting, lattice setting requires some of the secret information to be from specific distributions instead. So whenever you just do a simple addition at the end, you're actually leaking information about your secret information. Because now the distribution of your response relies on both the distribution of your key as well as your signature randomness. To avoid this, we usually do something called a rejection sampling, where we do repeat this process with some probability so much so that your distribution of your response is actually independent from your secret key material. We are already hitting stuff that are starting to be shady in a threshold setting. But surprisingly, we can just abuse the additive homomorphism we have, this type of scheme, to have nice, basic full threshold constructions. So you can just assume that everyone does this on their own, and you can just combine everyone else's commitments as part of the protocol and derive jointly a challenge based on their commitments and do rejection if needed, and continue to do everything as the same and be done with it. But now the problem here is, even with the simple extension and with the rejection, you're now sending information before you actually reject something. And now you're leaking information about your key even before. So if any of these signers are actually malicious, you have a target to attack vector. There are a lot of solutions to actually handle these. And one of the most key is the solution by Damgaard and all, and the extension of this generic basic construction into something much more serious. And the idea is you're just adding a partial public keys as part of your public information. And now, in addition to what you already do, you're instead committing to your commitment instead. And you also add a degree of randomness. So whenever you have to reject something, you're not actually leaking anything with respect to your commitment. With the cost that you're also adding additional randomness as part of your signature, and your actual signature verification becomes the checking of this commitment as well. One thing this allows is you can actually check if someone is cheating before you actually send the signature, something we call the idea of identifiable about. I have been rambling about the signatures for 7 minutes for now, and it seems like there is no problem here. But the actual problem comes when you actually want to extend this notion for any kind of threshold instead of trying to do a full-on threshold. So far, we have been using the idea of everyone trying to participate as part of this, so we can just use basic additive homomorphism and combine everyone's share sort of thing. But if you want to consider an arbitrary threshold, none of these happen easily. Because now, first, you cannot rely on someone being short on your own share to be having a resulting short share instead at the end, because all of the TR of n combinations cannot guarantee that if something is short on your side, it will be short on when you want to combine these values. Now this is an issue. Key generation is also an issue, because now it's not guaranteed that you can just simply do everything on your own without actually relying on some other people. And doing all of these, since we cannot guarantee that none of these shares are short, we cannot guarantee that we can actually reject something here, which constitutes a problem. And this constitutes the base of our research question we try to answer in this work. That is, can you actually find an efficient lattice-based threshold scheme that is applicable to any kind of arbitrary thresholds? And turns out the answer is yes. And surprisingly, it uses a mechanism I deemed inefficient at the start of this talk. So basically, Bonnet and some others introduced this idea of a universal thresholdizer, where not specific to signatures, but any kind of protocol can be turned into a threshold variant if you can just pass this through this tool called the universal thresholdizer. And the idea is you have your protocol and you just decompose this, embedding the secret information inside of it as a circuit. And you just pass the circuit throughout the universal thresholdizer, which includes a threshold fully homomorphic encryption with some non-zoned proofs and homomorphic signatures. And at the end, you have a threshold version of what you want to have, which is a quite nice idea. And you can just immediately see how you can make a threshold signature out of this. You just consider your circuit to be the signature circuit. You just embed your signing key and be done with it. But the problem is, since we are using a Schnorr-like signature, now this means that you have to do both the challenge generation as well as the rejection over ciphertext, which are distribution independent. And it's quite heavy to go through all this process over full-on FHE. But the idea of using FHE as a subprotocol is quite interesting, because now you can hide if someone is leaking information about part of the thing. And this begs the question of if we can salvage any of these ideas. And turns out it's yes. In our idea, instead of trying to run the entire signature circuit over FHE, we just use FHE as part of the signature to hide relevant parts so much. What we do is a linear computation of an encrypted signature, which we then decrypt as part in a threshold manner. So when you actually want, what you do is you combine the idea of a universal thresholdizer with the nice linear properties of the Damgard-like protocol. And what you have is something that's linear and that does not rely on full-on black box execution of a signature. So during a key generation, what you do is you start as if you were doing a key generation on a Damgard-like full-on threshold signature. But now, instead of generating a private key, you just generate a private signing key in an encrypted form. That is to be used later instead. Then your threshold decryption keys become your actual threshold signing keys. And you want to sign something, you continue as if you were doing a Damgard-like protocol to compute your signature randomness, but now you also compute it in an encrypted manner, so you can compute an encrypted signature at the end. So your partial signatures become the partial decryptions of the signature, and you can finally combine them to have the same signature at the end. This allows us to completely evade black box execution of an FHE and just use the relevant parts on the signature execution. So we can just use the TFHE designed in Bonnet paper and be done, right? Turns out no, because threshold FHE is something not trivial and has a lot of issues on its own. First of all, we didn't solve the issue of key generation in this case. We just delegated it into threshold case and assumed that we somehow have access to threshold keys. But out of the box, TFHE does not have any kind of distributed key generation, which was what we need as part of our signature algorithm. So much so, the other thing is the security notion of the TFHE in our setting specifically is unclear. The simulation security is too strong, and whenever you want to go to game-based security, there is not an exact definition that matches our needs based on what we have so far. And since we are trying to rely on Shamir type of secret sharing, now all of the bounds are all over the place for each of our shares, and we have to handle them as part of our key, otherwise we will still be leaking information about ourselves. And finally, something we overlook still that I still haven't mentioned is we haven't dealt with the rejection as part of our signature. So in our work, what we do is we first build a suitably threshold linearly HE that's not full FHE, but just linearly homomorphic, so we can just skip some of the inefficient parts as part of our thing. Then we avoid our rejections sampling in our base signature, and combining these two, what we get is a threshold signature that is suitable for any kind of arbitrary threshold. So to build the threshold HE, which first defines this new notion of indistinguishability. And when you just look at it, it is basically a weaker notion than a standard type of indistinguishability or any kind of simulation-based security. But you are allowed, you as an adversary are allowed to query both the partial decryptions as well as the part of the key generation, but you are not, your queries are quite restricted in nature, because that's what we all need as part of our signature, not full-on homomorphic encryption security, but just something that's sufficient enough for our signature. When you just restrict everything like that, it's quite easy to actually build this type of linear HE. We just use BGP FHE as our base scheme, then we add a simple secret sharing based distributed key generation, something that can be considered as the lattice equivalent of the Peterson style key generation. And then we just use statistical noise flooding so we can hide everyone's partial decryption share, so we are not leaking anything about our partial decryptions. Then our protocol is quite simple. We just assume as if we were starting with a BGP FHE, everyone just samples their own secret information along with the error, derive their own public key, secret share everything, send everything else, and then combine everything as well. This is secure for any kind of passive adversary that's not interacting to maliciously prevent the execution of the community. And what you can do is just, you can use commitments and zero knowledge proofs to bootstrap this to active security. I'm going to skip over this for the rest of the talks. Otherwise, we will be here until the rest of the session. Similarly, for the threshold decryption, you start as if you were doing a decryption for the BGP, and now you also have to know who is participating in the decryption scheme. So we can avoid this issue with the Chemical bounds and the noise flooding in general. So everyone just computes the Lagrange multiplier for their own and continue alongside with the noise and continue to do their compute the decryption shares and linearly combine everything to get a partial decryption. So that solves one of the issues. The second issue we had was the avoiding the rejection sampling. So if you recall, the rejection sampling was there to prevent leaking information about secret information whenever you actually prevent the noise. So what we do is we just remove this in general, assuming that at each query, we are going to leak something about the key instead. But instead of assuming this is a scheme up until it, we just bound the number of queries we're going to make as well. This allows us to use an analysis based on linear divergence and use the same type of signature blueprint without actually relying on any kind of other machinery as well. This idea was previously also approached in Agrawal and other stuff, and the idea of gentle noise floating. Basically, what we do is we just increase the noise and the signature randomness so a bit, so we can just avoid rejection altogether. And combining these, our threshold signature scheme is quite simple in nature. We start as if we are doing the ring variant of Damgard style scheme, but first we run the key generation for our underlying homomorphic encryption scheme to get our partial keys as well as our encryption set. Then we continue the key sharing as if it was Damgard again, but now we also encrypt the secret information. So whenever we want to sign something, we can actually have encrypted auxiliary information we can use as part of the signing. In the end, the verification key remains the same, but our partial decryption keys become the partial signing keys instead. And for signing, in addition to our generic public information, we also have to know about both the participating threshold as well as this ciphertext we just computed as part of the key generation. And we continue as if we were doing a Damgard style signing. But now, in addition to what we have already done as part of our protocol, we also encrypt the randomness and send these randomness as part of the error. In the end, we can just compute an encrypted version of the base signature I discussed about, and then each of the partial decryptions become the partial signatures instead. And the final signature this way remains the same. And for security, it's funny that you can just show that this scheme has threshold unforgeability based on the unforgeability of this rejection-free signing, the indistinguishability notion of the homomorphic encryption, as well as ring LWE, and the underlying security of the commitments and the zero knowledge proofs, but that's only required for the active one. And how efficient is this? I actually didn't want to include this table before because it feels a bit aggressive for no reason, and the authors of the raccoon are already here and will maybe kill me. But basically, I wanted to show that how this weird notion of threshold security fares against others. And the idea is our bandwidth is worse than what you get, but this kind of approach allows us to have distributed key generation out of the box. They can also use our distributed key generation for this. And something they actually have is the idea of identifiable abort, where we can show that if someone is cheating, you can actually catch immediately who is cheating. So in conclusion, and I realize that I'm a lot of over time, basically we built a two-round lattice-based threshold signature that has distributed key generation and identifiable abort, and relying on a simple linearly homomorphic encryption as a building block, which may be of independent interest in other protocols. Our results can be considered somewhat practical, but comparable to both stuff presented in Eurocrypt and stuff we presented in crypto. And for future work, one thing I consider this work as is the a feasibility result of practicality. That is, you can do somewhat practical protocols using this approach. So yeah, and everything was built towards this protocol with this idea in mind, but there are still a lot of things you can actually optimize in terms of communication. Something I was considering so much from scratch was we assumed everyone being corrupted at the start and never actually expand upon that, which is not a realistic scenario. We would love to add adaptive security to this notion. And finally, something interesting is this type of framework could be considered as like a restriction of a universal thresholdizer, and we want to see what else you can achieve with this type of approach. Thank you, and sorry for rambling for 20 minutes.
Thank you very much for this great talk. Are there any questions?
You said you get rid of rejection sampling. Does that change the error distribution?
Yes, in the sense that we are just increasing the noise for the per signature randomness, but in essence, we are just leaving it as it is, just with higher parameters instead. Yes.
Mentioned you have to limit the number of queries.
Yes.
For leakage. Is that you to limit the number of signatures?
Yes, yes, but basically, so there are arguments about like what's the required amount of signatures, what you may have. Something is one-time signature, which is a base signature, but also NIST has an argument saying that 2 to the 64 signatures is basically infinite amount of signatures, which is also what we have as part of the values we consider as well. So basically, it is bounded number of signatures, but you can make it practically infinite number of signatures if you just choose your parameters accordingly.
And what happens when you go above that? How bad is that?
You just leak the key S instead. But one advantage of this, using this type of approaches, the key generation for the actual encrypted signing key is different from the encryption key generation. So you can just rerun this asynchronously once in a while, so you can actually do. But 2 to 64 is like practically infinite, yeah.
More questions?
Yeah. Does that mean that to actually be able to generate 2 to 64 signatures, you need the larger parameter set?
Yes. So basically, something I completely glossed over, and I don't know, and I don't think anyone actually wants to listen to how these parameters have derived this, but there is a square root factor when you want to calculate what the parameters look like, which is why you have higher sizes for signatures and keys when you go higher on number of queries you actually require.
Those points for the passive or active registry?
This is for active, but without the actual communication cost. That's the only final signatures because we want to consider what you would actually store rather than something you actually pass around. The main issue comes, just to add, when you actually want to do the communication, it's a bit higher because now we have to send commitments and proofs in the active setting as well. This one not, we have a follow-up paper that will be implemented.
Okay, thank you very much, Doruk, for this great talk.